we don't give it up. Those would be some very simple ones. Those environments still exist today. So these are our metrics. Now, we're going to be able to do a lot with these in terms of mimicking computer usage. All right? We're not going to be able to go, massively efficient in terms of using our processor, but it's going to get us a long way. Maybe it'll get us up somewhere around 80% utilization for a job that's running, for a process mix running on an average computer. There's other things we do to eke even more efficiency out. You can get pretty darn efficient. Okay. But we're going to look at basic algorithms, not enhancements to those algorithms. Some of the algorithms, the way they get much better performance is through the use of hardware mechanisms that we might mention towards the end of the next class, but you won't be held responsible for on an exam. So, the CPU or long-running job is just one that primarily uses the CPU. We're going to assume that it uses the CPU 100% of the time. So when it's given the CPU, it can use it efficiently for the entire time that it has the CPU. Okay? We don't have to worry if it's 99 or 98 or 93.6% efficient. We're going to say it's 100% efficient on using the CPU. Once it's there, it will use it till either it's done or it gets kicked out of the CPU. Okay? The other one, interactive, is how we expect to use computers when we're sitting down. Okay? So, how many of you would feel really happy if when you sit down at your machine or your laptop at home or something like that, and you move the mouse, how many feel really good if it took 10 seconds for the mouse on the screen to start moving? Okay. How many would have said, one of you would have immediately said, was there an upgrade installed on my machine last night? We don't want that. Interactive jobs have this requirement for good response. Okay. Good response time to external events. Okay? And whenever we're dealing with an environment like that, processors spend a lot of their time waiting for those events to occur so that they can be efficient in responding to them. Thus, interactive jobs are characterized by only using a small fraction of the CPU time that they're given. And there's different things that we can do with that. But we're going to start on CPU bound. At the end of today, we're going to relax that, and we'll move into interactive jobs to do a lot of I/O, and mixing that with the CPU-bound jobs next time. Is comfortable with that? All right. Has anyone ever heard of the term batch? Batch processing. Batch processing is kind of weird. In its purest form, when the job comes in, we put it in the computer, it runs to completion, and it does nothing but calculations. Might even take in a little bit of input at the very beginning, spit out some results at the very end, but it doesn't waste time interacting with the outside environment, not even a disk, okay? Because in batch environments, very early computing, the cost of the CPU was millions of dollars. Okay? So the whole goal was to only give the computer tasks that could be done very quickly and over and over and over again. Okay? The idea was just to give it something that was essentially pure calculations. So the idea here is that in batch environments is that keeping the CPU busy is our primary concern. Okay? Not only that, we're just going to assume that there's no I/O done. Right? We all know that's impossible. Right? How many of you have ever run a program that all it did was give back the $ prompt, and you were like, yes, works. Okay? Did anyone turn that into Carla? Here's my test. I'd like to see you do that. I want to be there. So there's that batch environment. And batch environments are characterized by jobs running one at a time to completion. Okay? My job runs to completion. Then if your job is the next one, your job will run until it's completely done. It doesn't need the CPU again, and it exits the system. And then your job is able to run, and it will run until it's completed using the CPU. Then it will exit, etc. Does that make sense? Okay. So, in this environment, as we can probably well imagine, there are no users. No one's sitting at a keyboard going, submit my batch job. Now I'll wait. It doesn't work that way. Okay, you have no idea what the delay is for you getting into the CPU. Right? But that's okay, because that's how systems were used in the 40s, 50s, and early 60s. Okay, essentially, they were compute engines. They were much faster calculators.
So this is, we don't use this at all today?
Oh, no, we use this a lot. Okay, because it turns out there's some types of environments where this works out really quite well. All right? But it's hard to think about. It's like things on computerized assembly lines look like this. Some things like that, where we do one thing and then we do another. One thing to completion, another thing to completion. If you think of a welding robot sitting at a position on an assembly line, welding door frames for cars. Okay, it's going to come along, and it's going to follow. That's going to come along. It's going to follow its schedule for welding, and then when it's done, it resets itself. So when the next one shows up, it just runs the same program again. It doesn't weld two different doors at once. It doesn't have two welding rods. It does one thing and only one thing, well at a time. Hearing aids. Hearing aids. We want them to essentially just run one job, right? What about your pacemaker? Highly interactive, playing World of Warcraft, something like that. It turns out, Stuart's playing World of Warcraft.
Oh, no, I was going to ask about the new hearing aids that dynamically adjust.
Oh, well, I know the hearing aids. There's a company in town called Fry that a friend of mine used to be the low-level architect for back in the 80s. And I talked to him. It's like, well, what do the hearing aids do all day? He goes, listen. I said, no, they don't. He goes, okay, listen and talk, listen and talk, listen and talk. And so yeah, I mean, it's very interesting. Now, I like to use the pacemaker as an example for the following reason. Okay, pacemaker does more than just measure your heart and fire off periodically. In fact, these days, there's quite a bit they do. They come up with a little device, put it over your pacemaker, and get your history since the last time that you've been into the doctor. Okay? They can find out if it's been fired. They can find out if there's been any problems with the pacemaker. Okay? A friend of mine who has a pacemaker, had it for his entire life. He's in his 40s now. I think he got it when he was 7. His pacemaker can't tell him when the battery's about to die. He lost his job, lost his medical. They figured he went about 3 years without the battery working before they figured it out. Okay. Wouldn't it be nice if you could find out the battery life, how much battery's left? Okay. But still, this is a very limited environment. Okay. It's still a very limited environment, and it looks a lot like batch. It's starting to get into multi-programming, where we can have multiple processes running at the same time. Multi-programming is what we do today. Okay. We have multiple programs that are out there that can be scheduled into the CPU. whenever they have work to do. And so we'll call that multi-programming or multi-process programming. We are now at the idea of multiple processors, and one aspect of that is called multi-core. All right, in here, I said we're going to just say processor and core. We're going to make them equivalent because the way we're studying the operating systems, we don't care. Okay, we're studying them at a higher level of abstraction. But multi-processors and multi-core in the real world of scheduling algorithms, beyond what we're going to talk about, so you'll talk about some of it probably, I think, in CS533 if you go into grad school. And I might, we have a course in advanced concurrency that that guy retired, but if we get back to teaching it, we're trying to get his grad student to teach it. It will talk about things like, how does, in the presence of multiple CPUs on a single chip, does that change how we do scheduling and how and why? Turns out it does. It changes things dramatically. Okay? But we're not going to go into that last one. We're in a multiprocessor environment in QEMU for XV6, but we're going to talk about it as though all processors are equal. We're not going to have any specialized processors. Okay? So now, how are we going to make this all work? We're going to start out with 5 constraints on our environment. And these constraints are historical. They all existed at one point or another. We're going to release or relax the constraints in approximately the order in which they were relaxed in the industry as our hardware got better. So these constraints, really, when you come down to it, is based on what we could build at the time in hardware and how we could make use of that. It wasn't that long ago. The environments we're talking about 1950s. So, 60 years you don't think of as something, monumental in the history of some technology. But in the CPU and operating systems world, there's been many lifetimes that have occurred in that. Okay? Lots of hardware designs have come and gone. And most of those designs went away because they filled a niche, and then all of a sudden materials and manufacturing got better, and the niche went away. Okay? So the first constraint we have is that all jobs take the same amount of time. Okay? All jobs take the same amount of time. Every job is that long. Does not vary. Okay? How many of you believe that every job takes the exact same amount of time? It turns out that's unrealistic, but it turns out that's how it worked in the early days of computing. Okay? And it was because we paid for CPU time. All right? Let's use an extreme example. Let's say that you pay in half-hour blocks. Okay. We'll use a big number from the 1960s, $100. Okay, say $100 for a half hour. So these were called service bureaus. You would go into them and say, hey, I have a job to run. I need a half hour on the machine. And they're like, okay, we got you scheduled for 7:30. Okay, I'll bring the job by. They bring the job by, leave the card deck, usually is what they were. And then they would go away and come back the next day. Turnaround time was considered, quote, average turnaround for the human was overnight, usually, or 24 hours. The job might take substantially less than that. Its turnaround time might be fairly short. Okay? But this job finishes within the same amount of time, has some interesting properties to it. The first one is, well, let's just ask it this way. Has anyone ever had a program that didn't compile? Back in this environment, the first step of running your job was to compile it. So your program's turnaround time might be 7 seconds. But guess what? You paid for a half hour. You're going to still pay for that half hour. All right? Kind of good for the person that owns the system, right? They're like, overbook the system because someone's going to have some bugs and I'll be able to run more jobs. Now, are you going to run right up to 29 minutes and 58 seconds on your job? Probably not, because do you know what happens at 30 minutes? The system resets itself. You're gone. If you have not gotten in some way that you can communicate your results, too bad. It's gone. I worked as a computer operator in the mid-70s. And our system was set up, it would say expected runtime, would say 30 minutes. We'd go away. And it had these little kind of funky little bells that you really couldn't hear over the horrendous noise of air conditioners and all that. It would be a little ding, ding, ding. But you learned to hear it from a couple rooms away. And all of a sudden, you put a job on, you go off, you grab your candy bar and your Coke, nerds, and you start studying. And you'd be sort of waiting there for that bell to go off, because that's when you had to actually earn your amazing salary. I think it was $1.19 an hour. But the job could end early, or it could be terminated early. All right? But you still pay for the same amount of time. So, we'll see that makes jobs relatively easy to calculate. We're also going to have this one, and this is also batch, where jobs all arrive in the system at the same time. And when I was an operator in a batch environment, what we had was people came in and they had card decks, and they would come in and they'd place them in a slot. As they came in, they just put them in a slot. When it was time for us to run the jobs, we'd go out, lock the door so no more jobs could arrive, go inside the computer room, slide the door back, and we'd just start running them. Okay? Now, interestingly enough, that kind of tells us that all jobs arriving before we start doing any computing tells us that we can do our scheduling without using our computer. Like, that's how it was done. Someone would come in and say, hey, here's my job. We say, put it in the bin. The bin was marked 8. And they go, well, how long is it going to take till my job runs? You go, well, you're number 8. Nobody gets more than 30 minutes, so it's at least 4 hours out. And they go, okay, we'll be done by the morning. Oh, yes, I can guarantee you we will be done by the morning. In fact, I can guarantee it'll be done in 4.5 hours. Okay? Now, these two together give us a very interesting way of looking at scheduling. And we're going to see that when the goal was to keep the CPU as busy as possible, we're able, with these two constraints, to do very, very good job of it. Now, number 3 says, once your job starts, it keeps the CPU until it's done. Right? And that means that the job gets the CPU, has exclusive use of the CPU, until we're done with it. Okay? There's some problems with that approach that advances in hardware allowed us to deal with later. But once the thing to note is that once the job starts, the job has exclusive use of the computer. Now, there's a flip side to this. And maybe I'll put this in, because it just jumped up on me. If your program has exclusive use, your process has exclusive use of the computer, okay, and it needs to deal with some exotic piece of hardware, how does it get that to occur?
I/O interacting with
Yeah, okay, I/O, but who does the I/O?
an operating system. Yeah.
Well, no, once it's got the CPU, it's the program.
Yeah, it's responsible for it. Yeah.
It's impossible unless we write it ourselves. Okay, unless we write it ourselves. And that's what we did in the early days of computing. So we could use exotic devices. Some of those were called printers. Okay. Tape drives. Disks. All right. If you're writing an accounting program, how good do you think we expect you to be writing software to manage a hard drive so you can save your data? Turns out back in these days we expected it. It was reasonable for us to expect that, because that's the only environment you had. You wrote everything yourself. That's one of the reasons for operating systems coming along is because the whole issue of if you've got 500 jobs that can run on your computer, each one of them has to have the source code for dealing with the printer. And they might all, you don't hand out the source code, they have to write their own. Okay? And not only that, if one person finds a bug and fixes it, it only fixes it for their program. Starting to look like maybe we don't just want processes out there just running on the CPU. It turns out we're going to change what we mean by CPU as we go through the scheduling. Let's talk about the evolution of scheduling. Then we say, hey, we're not going to do any I/O. We're just going to throw that out because it complicates things. We'll relax that later. And then we say that how much time a job is going to take is known beforehand, known a priori. That looks like number one, but it's not. Okay, number one says they all must take the same amount of time. It doesn't say how much of that time it will use or if it needs extra.